Looking at further maths on the Pearson specification, we're looking at a proof by induction. Just for those of you who are not on the Pearson specification, then I'm sure this video will still be helpful. A lot of the things cross over in the specifications, and if you just want to learn maths, then you're more than welcome here as well. So proof by induction. Well, this specification in particular wants us to use proof by induction for summation proofs, for divisibility proofs, and some proofs with matrices. So we're going to do one example of each, and I've actually taken these from the specification list as the questions, so that they're not going to come up in exams or whatever. But these type of questions will. The first one we're going to look at is a summation problem, and we've got to prove that for all natural numbers n, so whole numbers that are greater than or equal to 1, that this sum from r equals 1 to n of r cubed is equal to 1/4 multiplied by n squared multiplied by n plus 1 squared. And our method for doing this is we show this is true for the lowest case, so in this case that's 1, and then we say, well, if it's true for some n equals k in the natural numbers, and then we write down what result that gives us, and then we say assuming it's true for n equals k, it's then, and we show that then it has to be true for n equals k plus 1, and this means that it's true for all, since we've shown it works for 1, so we can get 2 from our result, 3, 4, and you can just keep going like that. So we'll see this more clearly. Now we're going to consider n equals 1, and the left hand side would be the sum from r equals 1 to 1 of r cubed, and that's just 1 cubed, and that's just 1. Okay, and the right hand side is equal to 1/4 times 1 squared times 1 plus 1 squared, so that's the 1/4 times by 1 squared, so that's 1, times by 2 squared, which is 4, so 1/4 times 4 is 1. So this is true for n equals 1. Now we're going to assume true for some n equal to k, and if this assumption is true, then we have r equal 1 to k of r cubed is equal to 1/4 k squared k plus 1 squared. Alright, so that's our assumption. Now we want to consider n equal to k plus 1. So we're going to start on the left hand side, and we're going to try show that this left hand side here, when n is equal to k plus 1, is equal to, and the result we're looking for is 1/4 k plus 1 squared k plus 2 squared, alright, because if you substitute in k plus 1 for these n's, that's what you get. And we're going to try to show that that's true using the assumption that r equals 1 to k of r cubed is equal to 1/4 k squared k plus 1 squared. Okay, so hopefully that makes sense. So the left hand side is the summation from r equal to 1 to k plus 1 of r cubed, and we want to write this in terms of this, so that's equal to the sum of r is equal to k plus 1, so that's just one term, that's just substituting k plus 1 in to r cubed, plus the sum from r equals 1 to k of r cubed, and this is because all the sum from r to k plus 1 is the sum from r to k, but with one extra term added, and that term, as we'll see here, is just k plus 1 cubed, alright, and that's added to all this, but we, from our assumption, this is equal to 1/4 k squared k plus 1 squared. So we always want to keep in mind the result we're looking for, and if you can remember, I said that we want 1/4 k plus 1 squared multiplied by k plus 2 squared. So we've got a quarter here, so we're going to factorize that out, and we want k plus 1 squared, so I'm going to factorize that out. And now inside these brackets, what does that leave us here? Well, here we get 4k plus 1, and that's 4k plus 4. And why do we get 4? Because we factored out the quarter as well, so we have to multiply up by 4 to this term. And then here we're just left with k squared. And this factorizes. Let's just write out these first two terms again. And this factorizes to k plus 2 squared. Brilliant. Now we're just going to write this in a form that makes it slightly more obvious as the result we're looking for. K plus 1 plus 1 squared. Okay, and if you look at our result for n, if you put in k plus 1, you would get this. So we have now shown, and I'm not going to write this all out because it's going to be horrible for you and me writing on this board with this pen, but you would write out some sort of explanation. So you'd say this result proves that if our statement is true for n equals k, it has to be true for n equals k plus 1. And we have shown it's true for n equals 1, so it's therefore true for n equals 2 and n equals 3 and so on by the same logic. And it therefore has to be true for all n in the natural numbers. Okay, something like that. You can write. I'm sure there's a more concise way of putting it, but you have to be clear and in your statement. You can't, when you're doing these questions in exams, you can't just get to this result and go, there you go, brilliant. Oh, that's my answer. You have to qualify what you're working out. You have to write down a statement at the bottom explaining, or statements as you go along, whatever, but you have to be clear, and you have to have a finishing statement saying this is why this proves that it's true for all n.